Hi, my name is Ron Lohman. I'm here with my colleague Jamil Kawa, and today we're going to talk about one of the more exciting things with AI chipsets, and it's really dealing with the compute intensity and how to handle the power consumption problem. What are some of the trends that you're seeing from a technology standpoint to handle that?
We are trying to mimic the human brain, is the bottom line. The human brain as it stands today is still 10,000 times faster than the most fast supercomputer and much more energy efficient. You're talking about 20 watts or less versus 15 megawatts. So this is our goal. So artificial intelligence networks using things like spiking neural networks and other networks are data hungry and compute intensive. So architecturally, the von Neumann architecture has reached its limit in terms of bottleneck. No matter how much you parallelize, it's not enough. It's still power hungry, especially when you are doing any compute. The memory fetch of the operation is exceptionally power hungry. So first you need to bring the memory either close to the CPU or embedded inside, or the other way is to say the CPU itself, the computation is embedded into the memory.
And so what's one of the differences between near-memory computing versus in-memory computing?
Excellent question. So a less rigid architecture would be to take the memory and place it as close to the processing unit as possible. You're not as efficient as in-memory computing, but you reap most of the energy benefits of that architecture. Another small differentiating element, which is the emerging memories that allow themselves into huge arrays that are very power efficient. There, in-memory computing might make even more sense than near-memory computing.
Okay, so some of the traditional SRAMs have some things like multi-port memories and maybe
Yes.
some customization that can be done, but there's also some future memory technologies that are playing a big role here?
Absolutely. Let's talk first a little about SRAMs.
Okay.
So we're converging to near-memory computing because of the versatility. So for that, you need a weapon of register files, multi-port files, multi-port memories, and so on. And we have a huge array of such memory compilers already in the offering. But beyond that, as you mentioned, in artificial intelligence, you need to access more than one word at a time, deep words. So you need multi-port memories, and we are developing a slew of those memories as well.
Okay, so that provides the parallelism to get better power efficiencies. Can you expand more on some of the advanced memories that people are looking at in chipsets today?
Sure. So there is a whole class of memories. They're not new in the absolute sense. Some of them have been around since the early 2000s, but they are emerging with a new thrust in terms of their capability of being integrated with CMOS. That's a key element. Their capability for 3D stacking. They're being ultra efficient in terms of energy, and they have durability and retention times that are excellent.
So they've been around for quite some time. Are they ready for commercialization?
First, remember, we do SoC chips. So we need to build compilers to enable anybody who is integrating a certain amount of memory integrated with the CMOS in the metal stack to be able to have compilers to realize those. And we're working on that. We have done a lot of research and we continue to do that. But the other area is when you need a lot of memory and you're going to need a 3D stack. We are also working in our 3D IC realization technology on how to build stacks that will integrate layers of logic with layers of memory. And that's very exciting. It's still in its early stages, but it's so exciting and promising.
What about some of the future technologies?
We started working on STT MRAM compilers a couple of years ago, and we're making pretty good progress there. Furthermore, given that all additional memories that we talked about, CB RAMs, resistive RAMs, phase change memories, are all integratable with CMOS. We are working in the research area on finding ways to do efficient memory compilers for those.
Great. So it sounds like there's a really exciting development with respect to existing SRAMs and existing future memories and the compilers that Synopsys is developing. This is a really exciting time, and I appreciate you sharing your insights with us. To learn more, you can go to synopsys.com. Thank you.
Thank you very much. This is fun times to be working on such memories.
Yes.
Thank you.
Thank you.